You are watching AI Paper Slop, where we summarize the latest AI and tech papers. And today's deep dive is into a paper called RoPE Distinguishes Neither Positions Nor Tokens in Long Contexts, Probably, by Yufeng Du and folks at the University of Illinois and Amazon AGI.
Yeah, and if you are building or even just using long context LLMs right now, this is a massive deal.
Totally. I mean, if you're an ML engineer, here's the hard-hitting summary. This paper mathematically proves that rotary positional embeddings, so RoPE, which is like the absolute standard in models like Llama, Mistral, DeepSeek, it fundamentally degrades at long contexts.
Right, like it is mathematically flawed. As your context increases, the unnormalized attention score actually turns into a normal random variable.
Which is wild, and that shift causes RoPE to fail at its two main jobs.
Exactly. It loses position identification, so it literally can't tell if a token is near or far. And it loses token identification, meaning it arbitrarily flips attention scores between highly relevant and totally irrelevant tokens.
And we're going to get into why adjusting the RoPE base is basically a zero-sum game, and why throwing more attention heads or layers at the problem doesn't fix it.
Yeah, it's a huge shift in how we think about this stuff. Because, for a long time, the community has treated context scaling as this systems challenge.
Right, like optimizing flash attention or squeezing more VRAM efficiency so you can shove 128K tokens into a prompt.
Exactly. But the findings here show we are actually hitting a hard mathematical ceiling. And to understand why it fails, we really have to rethink how we analyze the mathematical behavior of that RoPE product, the unnormalized attention score across distances.
Okay, let's unpack this. So let's briefly recap what RoPE is actually supposed to do for those tuning in. It basically divides your hidden dimensions into two-dimensional pairs,
That's
right?
it. Those pairs rotate at different frequencies.
Right, so you have high-frequency components that oscillate really fast to capture those local position differences, and then low-frequency components that decay slowly to give us that global recency bias.
Which is supposed to preserve token relevance over a distance. But here is the paper's major theoretical breakthrough. Instead of just looking at that low-frequency decay like most prior research does, the authors apply the central limit theorem.
Oh, wow. To the entire RoPE product.
Yes, to the whole thing. They prove that if you randomly sample the distance between a query and a key over a large context, the RoPE product can literally be modeled as a normal random variable.
Okay, so a normal distribution.
Right. And the mechanics are fascinating. The mean of this variable decreases as the context grows, which is due to that low-frequency decay. But the variance actually increases.
Due to the high-frequency oscillation, right?
Exactly.
Wait, so as the context window stretches, it's basically like trying to detect a specific radio signal where the actual volume of the broadcast is fading, but the background static is simultaneously getting louder and louder.
That is a perfect analogy. And that exact mathematical reality, the decreasing mean and the increasing variance, is the root cause of every specific failure mode we are about to talk about.
Okay, so let's look at the first catastrophic consequence of that static overtaking the signal. The model loses track of where tokens actually are.
Yeah, which completely kills the recency bias.
Because normally you'd expect a model to have that bias. Like if you have a key token at position 100, it should get a higher attention score than the exact same key token at position 10,000, right?
It absolutely should. But the authors introduced this concept called position inversion.
Position inversion. Okay, what is that?
Well, because of that increasing variance we just talked about, moving a key to a substantially farther position can actually increase its attention score.
Wait, really? Just by chance?
Yeah, just by mathematical chance. And what's fascinating here is that as the context length grows, the probability of this happening literally approaches 0.5.
So it devolves into a coin flip.
Exactly. The model is just guessing. It has no idea which token is closer.
That is terrifying for long context retrieval.
But it gets worse,
Yeah.
right? Because of the hardware constraints. Oh yeah. This brings us to position aliasing. This happens when the difference in RoPE products between two different distances falls below the actual data type resolution limit.
Right, because most of these models use BF16, which only has, 7 explicit fraction bits.
Exactly, 7 bits for the mantissa. So it can't represent tiny differences when the overall magnitude of the numbers gets pushed up by all that variance.
It's like looking at two completely different shades of gray on an old monitor, but because the monitor only supports 16 colors, they render as the exact same pixel value.
Yes.
So the model is literally blind to the distance.
Literally blind. And the empirical proof in the paper is just staggering. They tested a single attention head on Llama 3.18b over just an 8K context.
Just 8K? That's tiny by today's standards.
I know. And within that 8K window, they found over 75,000 pairs of aliasing positions.
75,000?
Yeah, meaning if you take two key tokens at these aliasing positions and swap them, the attention output for the query remains mathematically identical, down to the bit.
So the model literally cannot see that you moved the tech.
Not at all.
Okay, so failing to know where a token is obviously bad. But RoPE combines position and token identity into a single dot product, right?
It does. They are baked together.
So that growing variance must destroy the model's ability to know what the token is too.
It absolutely destroys it. And this leads to token inversion.
Right. Let's use the paper as case study to make this concrete for everyone. Say the input has sentences like Alice has a cat and somewhere else Bob has a dog.
Okay.
And your query is looking for Alice's pet. We obviously expect the key token cat to score higher than a totally random token, like the word number, right?
Of course. And at distance 0, cat does score higher. But here is where token inversion kicks in. Within just 10 tokens of distance.
Wait, 10 tokens?
Just 10 tokens. The variance causes the difference in scores to drop below 0.
You mean the relevance ordering just reverses?
Yeah. And if you go past 20K tokens, the probability of the model randomly preferring the irrelevant number token over cat approaches 0.5.
Again with the coin flip.
Exact.
But wait, if the score can flip that easily just from the positional noise, does that mean the aliasing problem from earlier also applies to token identities?
It sure does. That is token aliasing.
So the hardware precision limit strikes again?
Yeah, because if you replace the highly relevant key token with a completely different token, the attention score can remain totally unchanged due to those BF16 limits.
Because the positional static is so loud, the hardware just rounds the semantic difference away.
Right. And in that same 8K range for Llama 3.18b, they found around 150 positions exhibiting this token aliasing.
So at those spots, the model effectively cannot distinguish between two completely different words.
It is entirely semantically blind there.
Man, at this point, I bet the ML engineers watching are probably screaming, just scale the RoPE base, or, the multi-head architecture will smooth this out.
Oh, I'm sure they are, because that is the standard industry practice.
Right. We just increased the RoPE base hyperparameter, like with NTK scaling in Llama, to extend the context length. So what does this all mean? Can't we just tweak the base and fix the math?
Well, the paper proves that this is a complete zero-sum game.
A zero-sum game. How so?
Because increasing the RoPE base actually does help preserve token relevance. It slows down the rotations, which lowers the variance, so it mitigates that token inversion and aliasing.
Okay, so we save the what?
But you directly and inevitably weaken the model's ability to distinguish positions.
Ah, because the rotation angles get so small that they fall right into the BF16 precision gap.
Exactly. You literally trade position failures for token failures. You mathematically cannot preserve both.
But what about redundancy? I mean, we are talking about models with over 100 billion parameters, dozens of layers, multiple attention heads per layer.
Right, the ensemble argument.
Doesn't all that routing protect the model from a single head failure? Like, surely the noise averages out.
You would hope so. But the authors completely shatter this hope with a real-world indexing task.
Let's hear it.
They asked models to find the kth element in an array of integers, just 0 through 3.
Okay, so token identification is trivial. It's a pure test of position tracking.
Exactly. And they tested Llama 3.1, 8b, Mistral 7b, Qwen 3, and even massive models like DeepSeek v3.1 and GPOS 120b.
Models that claim context lengths of 128K or more.
Yeah, and the results are just brutal. Despite all those claims, all these models plummeted to near random guessing accuracy, which is around 0.25 for 4 options at just 4,000 to 10,000 tokens.
Wow. So at 10,000 tokens, the multi-head redundancy completely fails.
Because the mathematical bottleneck of RoPE is systematic. You can't average out an error that is baked into the fundamental geometry of every single attention head.
That is just wild. So the ultimate takeaway for everyone watching is that those recurring failures we see in long context tasks like the lost in the middle problem or massive drops in needle in a haystack evaluations, they aren't just a lack of training data.
No, not at all. Or poor engineering.
Right. They are an intrinsic mathematical limitation of RoPE itself.
Which is a tough pill to swallow for the industry.
It really is. And I want to leave you with a final, somewhat provocative thought to ponder. If RoPE fundamentally degrades as context scales, and extending the nominal context limit doesn't magically fix the underlying positional mechanism, what does the future architecture of LLMs even look like?
That is the big question.
Because if multiplicative positional embeddings like RoPE are a dead end for true infinite context, will the community have to pivot to dynamically routed positional encodings?
Or maybe entirely position-free causal transformers.
Exactly. Are we going to have to break this mathematical ceiling by throwing out positional embeddings altogether? It is something to keep an eye on. Thanks for watching AI Paper Slop, and keep questioning the architecture you build on.